Welcome back to those of you out in YouTube. This is the fourth in a five-part series on Darwinian Agriculture at the International Rice Research Institute. And I've been arguing so far that natural selection may have missed some opportunities to improve the collective performance of plant communities because those options would have decreased the fitness of individual plants and therefore would not have increased by natural selection. So since what we're really interested in is the collective performance of crop communities, should we question nature's wisdom or natural selection's wisdom and explore some of those options? I argue that we should, and in my last talk I discussed some of the cases where there are trade-offs between individual fitness of plants and the collective performance of plant communities, trade-offs which, if we understand them, may lead to relatively simple, genetically simple options for improving crop performance. Uh-oh. I am not getting slide advance here. Just use that. So, so today I'd like to discuss three additional options beyond the ones I talked about yesterday. The theme of my talk today is more trade-off-linked opportunities. And these are the three cases that I'd like to talk about. First, whether it's possible to get both higher yield potential and better suppression of weeds by a crop. Second, possibilities for increasing water use efficiency of a whole crop community that stem from looking at water use efficiency as a public good as opposed to an individual fitness trait. And finally, the prospect for developing crops which would improve conditions for the next crop in a sequence. And the particular example of that I'll give is based on interactions between crop plants and microbial mutualists and conflicts of interest between those two parties. So starting first with yield potential and weed suppression. I've showed this slide a couple of times already, and what it shows is the disappearance of a high yield potential genotype when it has to compete with lower yield potential genotypes that happen to be taller or have more horizontal leaves or more branching, more tillering, etc. Data for both barley and for rice. And so from this kind of data and from the arguments in Colin Donnell's paper where he talks about trade-offs between individual fitness traits and the collective performance of plant communities, based on those kinds of data and arguments, I assumed up until a couple years ago that there was this inevitable trade-off between the competitiveness of crops with weeds and the yield potential of those crops. So obviously you could get a crop, you could get a genotype that was bad at both by having, a terrible root system or whatever, but that it really increased the yield potential. I assumed we were going to have to sacrifice the ability to suppress weeds and therefore perhaps have to rely more on herbicides. But Jacob Weiner, I think is originally from the US, but has been working in Denmark for a number of years, also a fan of Colin Donnell, but has taken Colin Donnell's arguments in an interesting and different direction than what I my book. Fortunately, I became familiar with them in time to include them in the book. And so he, like Colin Donald and me, and I guess probably Peter Jennings here, argue that natural selection, and John Harper, others, Casey Witt, argued that natural selection favored individual plant fitness over plant community performance. So we're all in agreement about that. But his argument is that individual plant fitness isn't necessarily exactly the same as the ability to compete with and suppress weeds. That when a plant grows taller in the presence of competing plants, that it's doing that really to get itself out of the shade and not so much to suppress the weeds, and that to a certain extent suppressing those weeds is somebody else's job, something that would benefit everyone, but that isn't worthwhile for an individual to do if there's an individual cost to doing that. So he says that there isn't necessarily a trade-off between yield potential and competition against weeds, that weed suppression may be a public good, something that wouldn't be favored by natural selection, but that should perhaps be favored by plant breeding or biotechnology. And here's his logic. The idea is that we do, in order to get high yield potential, we are going to have to sacrifice the ability of wheat to compete with wheat. But that we don't necessarily have to sacrifice the ability to compete with and suppress weeds. And so certainly for wheat and perhaps also for rice, certainly for a number of crops, the crops often have larger seed size than the weed species with which they're competing. I don't know if that's true for rice in all cases, but it's often true. And to the extent that's true, that means that shortly after germination, when you have little seedlings, that a little seedling of a crop plant is going to be more competitive than a little seedling of a weed plant that's drawing on a lower resource supply from smaller weeds, from smaller seeds. And therefore, what we really want to do is, at that early stage, when you have a little crop seedling, have those crop seedlings not interacting with each other and suppressing, the growth of their fellow wheat or rice plants, but rather interacting with weeds and suppressing the growth of those weeds. And to do that, he suggests a combination of high crop density, something that we've been doing for various reasons, but also very importantly, uniform spacing of the crop plants is going to, if crop seedlings are arranged in rows, as in wheat, or if they're arranged in hills, as in rice, then very early in their development, you have rice competing with rice, or wheat competing with wheat, and meanwhile, the weeds are at some distance away, many of them, and not being suppressed by the crop. So uniform spacing is important. So that's the agronomy, and then the associated plant breeding is to modify the phenotypic plasticity responses of crops to crowding, because it suggests that those may not be optimal in terms of weed suppression. So here's some actual data from the agronomic part of his hypothesis. So the vertical axis is wheat biomass, so higher values are bad, like low wheat biomass. The horizontal axis is crop seeding density, so as you go to the right, you're putting down more seeds per square meter. And then the two lines reflect two different seeding patterns. The upper line, the one that has more weeds over a range of crop densities, is the traditional system where you have wheat planted in rows, so you have wheat plants competing with each other very early in their growth, but not competing with weeds that might be in the middle here. And then this lower line, which has lower weed density, which is good, is this uniform planting pattern, where you would not have as much early competition between the wheat plants, but they might be closer to the weeds and suppress those weeds. And then for the crop breeding, genetic improvement part, he hasn't done that yet, but he has these, called my attention to these data, which I think are for maize. The horizontal axis for both of these graphs is days after emergence. The upper graph is plant height, and the solid fill circles are a weedy situation where the crop is receiving these red, far red crowding cues from the weeds and responds early on by an increase in height. You see the weedy plants, crop plants taller than the non-weedy ones. But that increase in height has a cost to the plant, and the net result is that if you look later on in the season, the crop is actually fallen behind what it would have been if it hadn't elongated so much early. And then down here we have a graph of the number of leaves, and we see again that the phenotypic plasticity response to crowding has resulted in, well, in combination with whatever the effects of the weeds are, I guess, has resulted in fewer leaves than in the absence of that response, or at least in the absence of weeds. So he's suggesting that it may be possible to modify these responses in ways that wouldn't have been favored by natural selection in terms of individual fitness, but that might give you better weed suppression. Well, I guess I would say that this, his arguments about what kind of response crop plants ought to have to crowding, maybe the evidence for that is not quite as clear-cut as the evidence for the benefits of a more uniform spatial planting pattern and higher density, but at least something to think about. And so I've tried to translate this into rice. I'm throwing this out for an idea for all of your rice experts to consider, not saying that I, having only worked once with rice and then only with little tiny seedlings that I used to test my laser tricorder for measured leaf area index. Interesting story, but I won't get into that. Anyway, this is my idea about how this might work. If we look at current planting patterns, you have perhaps 4 rice plants planted together in a hill and 20 centimeters between hills, and then I've dotted out a bunch of random weeds. Now, I was actually been impressed in your flooded fields how few weeds you have, so I'm not sure how big of a problem this is, but if you think about direct seeding, you might have more weed problems. Anyway, let me run through my very simple-minded simulation of this process. So this is at early growth. This is a little bit later. The rice plants are getting bigger, the weeds are getting bigger. And at this point, you can see that the rice plants are competing fairly strongly with each other, suppressing each other's growth, and yet they haven't interacted at all with the weeds yet, so the weeds are growing unrestrained by any competition with the rice. And only much later, when the rice plants are really getting in each other's face, you start seeing interactions with the weeds suppressing the growth of those weeds. And so my translation of Weiner's ideas into rice is to plant individual plants rather than groups of plants in hills, put them closer together, and I've used 10 centimeters here. John Sheehy and I had all sorts of conversations that, well, this stems per plant issue and spacing issues have been explored quite a bit, so I'm not sure how much of this is new or useful, but let me go through it anyway. So now we start seeing, again, growth of the rice plants, growth of the weeds, which I'm assuming are, in both of these simulations, are growing slower because of smaller seed size. Go a little bit further, and now much earlier than with the previous planting pattern, we're getting these interactions between the rice plants and the weeds, but no competition, no interactions between the rice plants suppressing each other's growth. And here at this stage, I'm showing a lot of weeds having had their growth suppressed by interactions with the more vigorous rice plants, and still we're at the stage where there hasn't been any competition among the rice plants. So maybe this is something you've already thought about, but if not, I'll throw it out for your consideration. And certainly, if you want to do this, you'll be thinking simultaneously about what kinds of genetic changes, what kind of phenotype and phenotypic plasticity do we want in rice plants to work best in this management system. And that would be true, that's certainly been true for what you've done in the past. I'm sure that's going to be very true in the future, that increase in yield and increase in water use efficiency or resource use efficiency is going to involve a combination of agronomy and plant breeding. And my impression is that International Rice Research Institute is probably one of the best places in terms of having those kinds of constructive interactions across disciplines. So Lichter doesn't yet have is genotypes that are optimized for this system, but they actually have a grant, which I guess I can reveal. I was a reviewer on the grant proposal and said I thought it was a good idea. So they're now actually working to develop plants with different responses to the shading cues. So they've got shade cloth here that mimics the kind of light environment that plants might be exposed to when they're shaded by neighbors. They're developing hardware for doing their more uniform and closer high-density planting. This is a field example of some of their tests. So, you could wait a couple of years and see whether it works with wheat before deciding whether to try this with rice. So I think their work is really interesting, and if you invite speakers from outside, often as you've done with me, this might be somebody to consider. So now turning to water use efficiency. So I showed this slide already with yield corrected for the metabolic cost of making more protein versus more starch, and water use in evapotranspiration, and data for Erie. And this set of data has rice and soybean and mung bean, I think maybe another C3 plant. And so we see there really, anything that falls on this line is essentially the same water use efficiency. So this makes it look like there isn't all that much variation. If there's not much variation in water use efficiency among species, how much would you expect to find within a species that you can use for improvement? So this looks kind of discouraging, and yet this is a paper from work by I think Roberts was the plant breeder, but a number of authors were involved in this project, and this is a successful example of development of high water use efficiency wheat, and the vertical axis is the yield of this dry scale wheat relative to a check variety at the same location. So 100% means there is no difference in yield of the two. The horizontal axis is the yield of the check variety, so that's basically an index of how dry things were at the particular location. And in the driest locations, dry scale has 40% higher yield. Boy, that seems pretty good. As we go to wetter environments, the yield difference declines, consistent with some kind of a trade-off perhaps between wet and dry conditions, but the point where it hits neutral, no yield difference relative to the check variety, is basically the environment, the wettest environment that would frequently be used for wheat production in Australia. So even though this suggests some kind of physiological trade-off perhaps, from an agronomic point of view, if there's no environment where this Drysdale wheat does worse, then there's no agronomic trade-off. And I think that's basically what I'm proposing here, is think about evolutionary trade-offs, physiological trade-offs, understand those, and using your understanding of those and how natural selection has favored individual fitness over the collective performance of plant communities, can we find systems where there's no agronomic trade-off? A yield benefit or drought tolerance or whatever without an agronomic trade-off, or at least with a trade-off that's relatively minor that we're willing to accept. And that seems to be what these people have done. But how did they do this? So that's so water use efficiency, agronomic water use efficiency, can be a very complicated sort of thing. But if you look at this at the level of the individual leaf and sort of a physiological definition of water use efficiency, it's really very simple. Somebody told Stephen Hawking that every equation in his book would cut his readership in half, so he limited himself to one. I was only able to limit myself to two in my book, but this is one of them. So the physiological water use efficiency is the ratio of photosynthesis to transpiration, evaporation of water from the leaf, and the photosynthesis rate is proportional to the difference in CO2 concentration in the atmosphere and the CO2 concentration inside the leaf, specifically at the inner surface of the stomata. So that's what's driving CO2 uptake into that leaf, is that concentration difference, just like Ohm's law, voltage difference drives the movement of electrical current, or movement of water through a pipe driven by pressure difference. It's all the same mathematically. And is this something that we can improve? Well, I hope you're all working on this one. Working to increase the CO2 concentration in the atmosphere. That will increase water use efficiency, and you can do that by driving your car more or whatever. Of course, there are negative consequences of that increase in CO2 as well, such as increased temperature, and that actually will undermine some of the benefits of increased CO2. The other thing that certainly what a plant breeder might be able to do to increase water use efficiency is to develop materials that would hold the CO2 concentration inside the leaf lower. Does this seem weird that lower CO2 concentration in the leaf corresponds to higher photosynthesis? But it's basically it's pulling CO2 with the leaf, and you can think about, suppose you had a glass of water and you wanted as much heat as possible to flow into that water. Well, you would get more heat flow into ice water than into warm water. Basically the same deal here. So how can we get a leaf that pulls internal CO2 lower? Well, one way is to make sure that we have plenty of rubisco. And from an agronomic point of view, one thing you need to do to make sure you have plenty of rubisco is to make sure that the plant has plenty of nitrogen. A plant that's nitrogen limited won't have enough rubisco to pull the CO2 low inside the leaf, and therefore it will have lower CO2 flux into the leaf, and CO2 flux into the leaf is exactly equal to photosynthesis, by just conservation of matter. But certainly in industrial agriculture, we already have high nitrogen levels, and there may not be too much room. John, am I wrong from what we said this morning? Not putting enough nitrogen on rice, perhaps, I don't know. But leaving that aside, what can be done through plant breeding? There has to be any number of mutations or genetic differences that would affect the ability to pull the CO2 level low. The question is, has natural selection missed any of those? Maybe not, because certainly high photosynthesis and high water use efficiency, all else being equal, has probably been beneficial throughout the 100 million year history of the wild ancestors of rice. And so, there may not be that many opportunities to improve that. But then again, who knows?